Hey everybody, video number 2, unit vocabulary for kinetics and equilibrium. We need to be able to define the specialized vocabulary of the kinetics and equilibrium unit. And I think that was missing out the last video, but that's another learning target, of course, for the unit, and it's one for every unit. So first, kinetics. What is kinetics? Kinetics is the study of how fast. So you see the particles are moving around? The rate of reaction. The rate. You know a little bit about rate. It's like distance versus time is rate. Okay. In this case, it's how much is reacted versus time. So the rate of the reaction is what we call kinetics. Okay. The reaction rate itself is how quickly a reaction occurs. This is the time versus reaction progress. Kinetics is kind of the study of that. Okay. And you got to make sure you don't get those two definitions confused. Okay, collision theory. See here, things are colliding, and this thing is counting how many collisions that happen in so much time, and they change color sometimes when they collide. Okay, the idea that describes collision theory. The idea that describes what it takes for a reaction to occur. It starts with a collision of reactants. And then we will define what that collision must be, and that's next. That's called an effective collision. We need to have an effective collision to make this reaction happen. So it has to have enough energy to actually break bonds and reform bonds. And we're going to get into the three or four things that have to happen. So this is the collision of reactants with enough energy and proper orientation to start a chemical reaction. So there's collision theory, that we have to collide, and then there's an effective collision, which is the ones that count. They're the ones that make reactions happen. And they have to have energy and orientation, and we will get deeper into that in the bell work and in many lessons and some talks in class. Okay. Catalyst. This is represented here by the dotted line. This is what you're going to need to be able to draw. I've seen this on multiple Regents exams where they give you the curve. Whether it starts low and finishes high or starts high and finishes low, that's okay. But the dotted line represents the alternate pathway that the catalyst provides. It is one way to speed up a reaction. It is not what I want to be your go-to answer, but we'll get into that. So this is a substance that speeds up a chemical reaction, but is not consumed by the reaction. You can include there, if you'd like, by providing an alternate pathway. We'll get there in the notes. Okay, but for our purposes for unit vocabulary, strictly a catalyst is something that speeds up the reaction but is not consumed. So therefore, it's still there when the reaction is done. Otherwise, I would be changing the reaction if it was consumed in some way. Okay. Thermodynamics. Thermo means heat. Okay. This is the study of entropy and enthalpy in chemical reactions. Enthalpy is heat of reaction. Entropy is randomness. They sound a lot alike. Enthalpy is that delta H. It has the H in it. That's how we remember. And entropy is delta S, and we will learn about that at the last video. Okay. Potential energy diagram. Here is one. Here is a common blank one where you have to fill in what those 1, 2, 3s, and 4s are. That's part of what we will learn to do this year, or this unit. Potential energy diagram is a graph showing the difference between the potential energies of reactants and products. Now, there's a lot of key words in there. Potential energy diagram. Diagram goes along with graph pretty well. And potential energies. Difference in potential energies. So potential energy diagram is a graph of potential energies. That one should be one that you get on the vocab quiz pretty quick. Okay. Delta H, heat of reaction. Okay. This is specifically defined as the change in enthalpy of a reaction. Notice the word enthalpy is in this definition. Hence, it's not the definition for enthalpy. Notice they're both delta H, the same thing. They have different nuanced meanings, but delta H means heat of reaction, delta H means enthalpy. So heat of reaction is the change in enthalpy of a reaction, the potential energy of the products minus the potential energy of the reactants every time. Enthalpy, okay, this is the heat of the reaction. Potential energy of the products minus potential energy of the reactants. Notice it's the same thing. These are found by looking at potential energy diagrams for table H. Okay, I strongly suggest you realize that the definition for heat of reaction is not going to have heat of reaction in it. And the definition for enthalpy is not going to have enthalpy in it. And this is how you get it straight. Okay, it's a very nuanced thing. Notice that the definitions of these two things were very much the same. The potential energy of products and potential energy of reactants were in there. Okay, because notice they are both delta H. They're the same. Two words mean the same thing. So we need to make sure that we know that both of them can be used synonymously. Okay? Entropy is randomness, the measure of disorder. So more disorder is higher delta H, more order lower. I'm sorry, delta S. So the measure of disorder in a system. Thermodynamics laws favor greater disorder, and this is true for the entire universe because there's less energy in disorder. I have to put a lot of energy into order things up. To keep your room clean, it takes energy, right? Keep it all organized, keep all your stuff organized, that takes energy. And the universe doesn't like to use energy. It wants low energy. Here's a very new topic for this unit, and this picture is going to be the same because of what's happening is this is the definition of an equilibrium. So we'll see this picture a few times. The forward reaction is going from A plus B to AB. The reverse reaction is going from AB, breaking it apart, and that's really what gets into what an equilibrium is, and we'll explore this in depth, I promise. The forward reaction is moving from left to right, reactants to products. That's what you need to know. And then there is something called a reverse reaction for reactions that are reversible. Again, same picture, because this is going forward, then reverse, and forward, then reverse, and forward, then reverse. And the reverse reaction is moving from right to left, going from products back to reactants. Okay? The activation energy. This is the energy needed to get to the top of the hill. So you see it's in the far or the largest black arrow. From the bottom of the hill to the top of the hill, the energy needed to get the reaction going is the activation energy. So this is the energy needed to get from reactants up to what's called the activated complex. Now notice the word activated complex is in this definition, so it's not the definition for activated complex. The energy needed is the energy. The activated complex is this actual point, that top point, which is the highest point on that hill, if you will. This is the point where reactants reach maximum energy along the reaction path and begin the formation of the products. Okay? We're not going to get into the complexity of the complex, I promise. You just need to be able to find out where it is. Fair? And we will leave it at that. Equilibrium. Look, this one's not broken. How fun. That's what it does. Newton's cradle. This is a state where reactions are happening in both the forward and the reverse reaction or direction simultaneously. That means at the same time. We show this in equations with a double-headed arrow, or a lot of times you will see an arrow this way and an arrow underneath it going the other way instead of it having two ends. How I draw it is one this way and one this way. It'll look like an equal sign, except for it'll have arrows on the end. Okay. Physical equilibrium. This is going to get into the three different kinds of equilibriums. We talked that we will do that. Okay, so physical equilibrium. This is a phase equilibrium. Notice physical equilibriums are a phase equilibrium. The rate of the melting equals the rate of the freezing. The rate of the evaporation equals the rate of the condensation. Okay, notice that the rates are equal, and I underline those. It's very important that we understand in an equilibrium, it's the rates that are equal. Okay. A chemical equilibrium happens in chemical reactions that can go backwards and forwards. This is a reaction equilibrium where the rate of the forward reaction equals the rate of the reverse reaction. Notice that rate is both, underlined in all caps. Probably should bold it, right? It's the rate that is equal. That's one of the things I need you to know for this entire unit. That is a big, big idea. Okay. Solution equilibrium. Now this is when things don't dissolve all the way, and we saw this with weak acids and bases. We got a little bit into the equilibrium during the simulation. Okay, so a solution equilibrium example of the dissolving equals the rate of the recrystallization. So if we get a solution that is saturated and you have too much sugar at the bottom, some sugar that's at the bottom will dissolve. And every time one of those molecules of sugar dissolves, another molecule that is dissolved must come out of solution. And they kind of force their way in and force their way out, but the rate is the same. For every one that dissolves, one crystallizes. Okay. Le Chatelier's principle. This is a picture of a Knox tube, which I do not own. I do not have possession of one of these things, but it changes colors from hot to cold. And you'll see maybe in this gift that it actually changes colors a little bit. It's getting lighter and lighter and lighter. Okay, classic lab experiment. This is probably the single toughest part of the unit. And this is a reaction at equilibrium will shift to regain equilibrium. We will get into this equilibrium stress and shift next, and that's what we need to work out. And we need to be able to figure out what's what, and am I going to favor the reactants or the products? Okay. So equilibrium shift and stress. This is a change in concentration, heat, or pressure for gases, causing an increase in products or reactants. Which way is it going to go? Le Chatelier's principle helps us predict. Okay, the actual change in stress or shift is this definition. Yeah, I've got my fingers crossed. That's it. We're done. We're done. So study your vocab words. Notice that some are different, some are really the same. Some are very the same with slight differences. So I want you to pay careful attention when you take this quiz so that you can pass it in your first try. All right. See you in class.